Hello, everyone. We're going to discuss section 1.4 on measurements today. I wanted to do this one a little bit differently than we did the first few sections because we are doing some of this in person and during the lab, and some of it will be here online. You should have this done prior to our lab on uh, the second the second lab meeting we have in the first week, so that you're ready to go with what we do in that lab. I also wanted to do this in this way because we're not covering actually everything in this section as part of this section, and a big chunk of it will be done during the lab time. So I want to kind of be clear about what parts of what's in your your online textbook are being covered now versus what will be covered as we get to it later. So let's go ahead and read through the learning objectives. We're not going to read, we're not going to just basically read the textbook, but I want to have it as a resource as we walk through these things. So the learning objectives, one, explain the process of measurement. I'll have a little commentary here. We'll be doing much of that by actually doing it during the lab meeting times. Second one, identify the three basic parts of a quantity. We're actually only going to get to two of these today. The third one will be, again, what we covered during the lab section. Describe the properties and units of length, mass, volume, density, temperature, and time, and perform basic unit calculations and conversions in the metric and other systems. We'll be doing a big chunk of this during the lab time, and we'll talk more about why we're doing it there on that lab day. So let's go ahead and get started with this. So I want to just point out a few things in this first paragraph. So this is where we talk about the three parts of a quantity or of a measurement. So there's three kinds of information that show up. The size or magnitude of the measurement. So that's basically, what is the number? So is it 1.4? Is it 25? Is it 32? Just whatever that number is only one part of it. So if you only have a number, you don't actually have the complete answer. And then this is saying a standard of comparison for the measurement. Basically, that's the unit. So a large part of what we'll be looking at today is what are those units, and it's always important to include those. And the third thing is the indication of uncertainty. We're not going to talk about that in this video. We will talk about that during the lab when we meet in person, because that's generally where we've gone through that sort of information. So those are the three things. So a number, a unit, and the uncertainty. We're not talking about uncertainty today. We'll talk about it during the lab. And when I say today, I mean by that as you're watching this. So there's some examples in here. We're showing this, so 298,000 kilograms. So this is the number, this is the unit, and again, we'll talk about the uncertainty later. So the units are, so we said kilograms was a unit. Let's talk about some units. So these are some typical units within the SI system. The SI system is the system of measurement that is used by scientists. It is also used by most countries in the world. We in the United States are kind of the exception, and we've been trying to move in this direction since I was a child and have not had success. So we still use miles and pounds, whereas in the SI system, units like meters for length are used. For mass, we would have kilogram. Second is the same, right, for time. Temperature is Kelvin. These first four are the ones we really mostly care about in this course. Actually, we don't even use seconds that much until the second semester. Electric current comes up in second semester. Amount of substance, we'll cover this in a later module. Luminous intensity, that doesn't really come up in this course, but it is another thing that could be measured. So these are the what we call the base units of the SI system. So we have the name of the unit, but we usually abbreviate those with a symbol. So you would need to know, if you see the symbol M after a number, is probably referring to a length with units of meters. Same thing, a kg means kilograms, S means second, capital K means Kelvin. So these are what those are referring to. Now, within the SI system, the reason why we prefer this in science is because of the unit prefixes that we use with the system. The reason these are helpful is because they let us scale to different size factors. So in the system we use in the United States, we might know how many feet something is, and we might know how many miles something is, but there's not an easy conversion between those. I happen to know it's 5,280, and I think the only reason I know that is I used to live in Denver, Colorado. But it's kind of a randomish number. Why would you remember that specific number? And then if you go smaller, the same thing, you'd have to know how to do that. And a feet to a mile isn't even that big of a difference if we think about kind of astronomical length scales, or thinking of going from macroscopic down to the size of an atom. We have very, very big changes. So the utility of the SI system is it lets us do that very easily by using these prefixes. Okay, there's a lot of them here. Some of you might recognize some of the ones down here based on your experience with computers or phones. I remember when mega actually was a big deal, and now we're talking giga and tera. So, bigger, faster for computers and cell phones. But we don't care about that for this class because these are big numbers. In chemistry, we look at small things. So let's talk about which of these we need to know. So we're going to start here with the nano. I'm going to go ahead and highlight these. So you need to know nano. You probably think of nano as being small. Nanos are very small, 10 to the negative 9th. So you need to remember that the prefix nano, which we abbreviate with an lowercase n, means 10 to the negative 9th. Maybe N9 helps you remember that. And this is an example of what that means. So if we have 4 nanograms, that means 4 times 10 to the negative 9th, and we could write it like that. Okay, so you need to know nano. If they want to keep getting smaller, you might see, pico phones or femto phones coming up. I don't know if they're going to market that or not, but these are areas of research, but we don't need to know them for this course. You need to know micro, so I'll highlight that one as well. Micro, we abbreviate this symbol that looks like a funny U, is the Greek letter mu, mu. We use for micro. Micro means 10 to the minus 6. So we're showing an example of that here. 1 microliter is 1 times 10 to the minus 6 liters. So nano, micro, and milli, you need to know milli. Milli is abbreviated with a lowercase m. So that means 10 to the minus 3rd. So 2 millimoles would be 2 times 10 to the minus 3rd mole. So we're showing here that scientific notation, 0.002. You'll notice for these first three, we go 9, 6, 3. Or negative, I should say negative 9, negative 6, negative 3. For most of the prefixes, we basically scale by an order by 3 orders of magnitude. So from -9 to -6 to -3. And you'll see the similar trend up here for these ones we're not doing. So that's true most of the way through. So if you remember these three kind of in order, milli, and then micro is, you know, 3 orders of magnitude smaller, and then nano even 3 more than that. So -3, -6, -9. We kind of run into a bit of an exception here with centa. Okay, so centa we abbreviate with the symbol C. So centa means 10 to the -2. So some of you might be aware that centa referring to 100. This means we have 100 centimeters, for example, in 1 meter. So that's what the -2 is telling us. So this is one some of us might be a bit more familiar with. So going from centa to milli, it's 1 factor of 10, 1 order of magnitude instead of 3 for these other ones. So these are kind of closer to our macroscopic level of when we actually kind of measure something with our hands with a ruler. We'll be doing it between these two. So that's why we aren't skipping 3, we're skipping just 1 in this case. We're going to skip the deci. We don't really need that for the most part. We'll be deriving something that uses that, but we're not going to worry about you memorizing it because we don't typically use deci. And then go to kilo. So kilo is the last one you'll need to know. So kilo we abbreviate with the symbol lowercase k, and it means 10 to the third. Okay, so these other 4 are smaller than, kilo is greater than, so by a factor of 10 to the third. So for example, 1 kilometer is 1 times 10 to the third meters, or we're showing that, you know, we can write out all those zeros. So we're getting bigger here, whereas the other ones we're looking at smaller and smaller and smaller. Okay, so these are the 4, or I guess 5. 1, 2, 3, 4, 5. These are the 5 prefixes that I would want you to know. You can use that same highlight function on your own textbook if that would be helpful to you if you're assigned into it. So this is a big part of this section is remembering these prefixes and then how to use them, which we'll talk about more as we get into section 1.6. We'll do a lot of 1.5 and 1.6 when we meet in lab, but I want you to know this information ahead of that meeting. Okay, so we have the prefixes, and then we have what are called the base units. And so for length, we're measuring distance, right? So we know what a distance is. We use meter for that, and then we abbreviate that with a prefix as necessary. So we could do, you know, meters just without a prefix, or here we're showing centimeter where we have a prefix. And we're showing here in this chart the relationship between the SI unit and the one we use in the United States. Just for the sake of comparison, if you are familiar with inches but are not familiar with centimeters, that's what that relationship is. I'm not going to ask that you memorize that relationship. That's something I have done in the past, and then I realized when I had students from other countries, they were actually having to learn something they didn't know with inches that wasn't even that useful to them. So I didn't find that to be so necessary to have people memorize that, but just for the sake of comparison. So mass is how much stuff you have. It's related to weight. If something increases in weight, it's increasing in mass. But again, weight is specific to the gravity field we're in, which on Earth we're pretty much always in the same gravity field. So it's pretty much always the same thing. We use kilogram in the SI system, and a kilogram is about 2.2 pounds if you want to relate that to English, although technically pounds is a weight and kilograms is a mass. But again, on the Earth, they're basically, we can say that that's true. And then in the lab, we aren't measuring things usually as big as kilograms, so we'll be using grams. often in the lab. Here we're showing, so by they I mean scientists are very particular about their measurements. This is an exact kilogram that's somewhere, and they have it specially stored to make sure it doesn't change, and then they can make comparisons. So they can have similar things to compare over the course of many years. Okay, let's talk a little bit about temperature. So unlike, say, mass is an extensive property, temperature is an intensive property, it doesn't change based on how much you have. In the SI system, we use the Kelvin, but we also use Celsius. And there's a relationship between Kelvin and Celsius where if you add 273.15 to the Celsius temperature, you end up with the Kelvin temperature. So they're related by that difference of 273.15. Usually 273 is close enough. So we'll often be doing things in Celsius. There are a few times, though, when it is very important that we do use Kelvin temperature. So we'll be very clear about when Kelvin is important and when it's okay to just use Celsius. The thermometers we use are measuring in Celsius in the lab, so oftentimes when we do measurements in the lab with thermometers, it's fine to use Celsius. And then we have time, which of course we are familiar with, seconds, and then we can convert to minutes, hours, days, years, etc. It's possible to do like megaseconds if you don't want to do years, but we're not going to get to that in this class, where we will see seconds come up a little bit, or time come up a little bit, but not that much until next semester. And we'll typically do seconds, but we'll have a few examples of conversions where you do use things like hours and days. Okay, so those are what we call the base units. And by base units, what we mean is we can't simplify it into anything less than that. So a length is just a length. You can't make length something simpler than what it is. Same thing with mass, same thing with temperature, same thing with time. We do have, however, things called derived units. And these are important. And the difference with a derived unit is that it can be simplified. It is more than one thing. So let's talk a little bit about some important derived units. And again, we'll spend a bit more time on this during lab. The two most important ones are related, and so we want to do volume first because the other one is based on volume. So volume is how much space something takes up. And what makes this a derived unit is that the space something takes up is based on lengths, right? So a length is not space, but it's, space is based on length. So in fact, space is based on length 3 times. So a volume can be thought of as 3 different lengths. So 3 different dimensions that something is occupying. So it's based on the base unit of length. The base unit of length defines volume. And you need essentially three lengths to define a volume. So we can think of the standard volume as being the cubic meter. So cubic meter means that you have 3 measures of length. So 3 meters are meters being measures of length. And we can write that m cubed, so m to the 3rd power. And how we can think of this, as we're showing in this picture down here, is we can think of it as a cube, and we have 3 different dimensions that we're measuring. So we have this dimension, this dimension, this dimension. So we can think of that as length, width, and height, for example. Now, which one is length, which is width, which is height? It doesn't matter how you define what those are, but just so that you're aware that there are 3 of them, and they are potentially different things. In this case, because we are dealing with a cube, they happen to all be the same. But we'll be, I believe, making some measurements in the lab where they could potentially be different. So we have the cubic meter. It turns out that for the sake of measurements, we want to make Another unit is more appropriate, and that is something we call the liter. It turns out the liter is the same as a cubic decimeter. This is the one time we'll talk about decimeter, and you don't have to remember it after this. But a liter is the same as a cubic decimeter. And what you might see from this picture is if we go from here to here, that's or I guess I should say from this larger cube to this smaller cube, there's a big difference there. And it might be bigger than you would expect based on the definition of a decimeter. So going from meter to decimeter, we're only changing it by 1 order of magnitude. But this, so basically by a factor of 10. But this is more than 10 times smaller than this is. This is more than 10 times smaller than this is. And the reason for that is because it's not just one factor of 10. It's one factor of 10 per each edge. So on this edge, on this distance, we can say this yellow part is 10 times smaller than the whole thing, but also true in this direction, also true in this direction. So it's 10 times smaller, but it's 10 times smaller 3 times. And we multiply all of those together. So 10 times 10 times 10. So when we say it's meters cubed, we're multiplying those together. So 10 times 10 times 10. So it's actually 1,000 times smaller. So this yellow box is 1,000 times smaller than this purple box. And then if we go one more than that, we would have a similar thing again. So a factor of 10 between decimeter and centimeter. So this is 1,000 times smaller. A cubic centimeter is 1,000 times smaller than a liter. And essentially, if we went from the purple one to the green one, from the liter, or from the cubic meter to the cubic centimeter, that difference is a factor of 1,000,000. So a cubic centimeter is 1,000,000 times smaller than a cubic meter. Now, normally that's going from meter to centimeter would be 100, but when it's cubed, it's 1,000,000. And that's why we introduced this idea of a liter. It's kind of in between, and it's actually the amount we typically would want to be using is somewhere in this range. We don't typically deal with cubic meters of water. I mean, our water bill perhaps, but in the chemistry lab, we don't deal with that. We deal with liters and things a bit smaller than that. You want to be aware of the liter. And it turns out we're defining this in such a way that 1 cubic centimeter is equal to 1 milliliter. Okay, so this is a relationship you want to remember as well. So unfortunately, I can't highlight the image, but you want to know that 1 cubic centimeter is equal to 1 milliliter. And then the regular prefix, and we'll go back up to that up here, of milli being 10 to the minus third, does work for the liter. So going from 1 liter to 1 milliliter, that's, milli being 1 times 10 to the minus third, works there. And but if you try to think about it, well, cubic meter to centimeter, milli to liter, just remember that we're changing these by 3 orders of magnitude each time over here when we're doing it in terms of distances. When we use the liter, though, we don't have to do that. Okay, so just be aware of that. In terms of volume in the lab, we'll mostly be using milliliters, and you want to be aware that milliliters and cubic centimeters are the same thing. Some of you, I'll also mention, some of you may work in the healthcare field and might know of the unit of cc. Okay, that is the same as cubic centimeter, so that would also be the same as milliliter. And then the other derived unit we will focus on in this course is density. And density is based on volume, so I have to talk about volume first. Density is the amount of mass in a volume. And because we're dividing by volume, this ends up being what we call an intensive property. So it doesn't matter how much you have. Because of that, density is a property of a substance in many cases. So we're listing here some common substances. We're listing these are their densities. If you have, for example, pure gold, it's going to have a density of 19.3 grams per cubic centimeter. So if you're not sure if you have pure gold, you can find the mass, find the volume, divide, and see if you get that. And if you don't, then you don't have pure gold, and somebody might be in trouble. There's a story of Archimedes' principle where somebody had a crown that they weren't sure if it was made of gold or not, and so they hired a smart person to investigate, and what they ended up doing was, taking a bath and seeing how that changed, and then from there came up with a way of finding that. We're going to be doing some investigation in lab related to density, so we'll talk more about it there. So we're kind of getting a jump start on the measurement stuff, but a lot of this we will do in more detail in person in the lab. That's the right place to learn a bunch of this stuff. But I want you to mainly be aware of the prefixes. So you need to know those. And just kind of what these different measures are, what we would be measuring, volume, and then we'll do more on density when we get to lab. So that is the end of this section.